Hello, everyone, and welcome to your daily dose of DOE here at the 2020 Online DOE Summit presented by Staties. And today we are going to be going through strategies for sequential experimentation brought to you by Dr. Martin Besner. And let's see, a couple of things. Dr. Besner here is the Director of R&D here at Staties, and he lends his skills to the development of our software design expert, and also with various consulting projects and teaching of workshops, and has also co-authored the book Formulation Simplified: Finding the Sweet Spot Through Design and Analysis of Experiments with Mixtures. So without further ado, Martin, would you like to take us on now?
Sure. Okay, so thank you everybody for coming here. Yeah, as Greg said, my name is Martin Besner. I'm the Director of Research and Development at Staties. Greg, can you hear? Can you hear me just fine?
Perfect. Yep.
Okay, great. Yeah, so today I'm going to be talking, we're in the middle of this online DOE summit, which is kind of a new venture for us in these interesting times. So today I'll be talking a little bit about sequential experimentation. Now, for those of you that came here for lots of formulas and theory and kind of, something like a textbook style presentation, you're out of luck, because today I'm going to be mostly talking about, intuition, behind the concept, some strategies that you can use, some pictures. So if you're looking for something super technical, unfortunately today is not really the day for that. So this is a topic that's kind of near and dear to me, because I think it's very important. I've used it a lot when I've consulted. Unfortunately, I've never really found a textbook that adequately goes through this, or even academic publications, which I've never really found something that goes through this. But yet this is a case, actually doing DOE on a near daily basis, something I run into all the time. So I'll go ahead and just start by introducing kind of what is this whole idea of sequential experimentation and why do we care. And I did just want to point out, kind of before I go too far, if you have a question, feel free to write it in the question in the chat. We'll save all the questions for the end. Greg will just read them off. If you have any other more specific questions, you can feel free to email me here at this email address that I've provided here. Okay. So yeah, so as I said, I'll talk a little bit about the introduction and kind of, just some simple motivating examples. Just, I think when I show this to people, they often say, yeah, that's happened to me before. And I'll talk about some strategies just from a very high level. Later on in this year, we'll have some more tutorials and documents and videos that kind of go through this in more detail. So this is fairly high level. I'll go through an actual example that we did where sequential experimentation kind of saved the day. And then finally, I'll just wrap up with a few concluding remarks. So, so let's go ahead and get started here. Now, traditional experimentation, this is how pretty much every textbook I've ever read on the subject presents the design of experiments as, or DOE. So traditional experimentation, it's almost always, I've seen, taught as a one-shot approach. Okay, and what does that mean? Well, here's kind of a random typical textbook example that I pulled out. So what you would usually do is you'd start, you have a problem and you think, okay, well, maybe if I tinker these parameters, or if I adjust my mixture formulation a little bit, maybe I can improve my process, or whatever it is that I'm interested in measuring. So what a typical experimenter would do, a typical engineer R&D person, is they would choose some factors that they want to tinker with and kind of define the low and the high of each that they're willing to consider. Once these factors are chosen, that defines what we would call the design space, basically the region where we would be experimenting. And from that design space, we would go ahead and choose an actual appropriate experimental design. The textbook would say, okay, we need to compute the power or the precision to make sure that we have enough runs, or maybe to make sure that we don't do too many runs. So what we would do based on that is we'd either add or subtract runs, needed to achieve the target power or precision if we're doing like a response surface experiment. Then, the experiment would be performed and the data would be analyzed. After we have a statistical model built, we would use that for optimization, and we'd kind of try to figure out, okay, where is my sweet spot? What settings of my factors, of my parameters are going to give me a response that I'm looking for? Okay, and then ideally, if possible, take whatever your statistical analysis tells you and maybe do a couple confirmation runs independently just to verify that everything checks out. Okay, so this is how things are usually taught, and then it all just ends up working out nicely. Now, I'm going to zoom in a little bit on two of these points that I mentioned. A lot of textbooks offer really no practical advice on these following two steps. So compute the expected power of the experimental design, but really it's more of this one: add or subtract runs needed to achieve the target power or precision. In my experience, I mean, rarely is there an unlimited run budget available, or people can just keep adding runs until they hit this magical threshold that's floating around. If you read kind of the DOE literature from a statistical point of view, it always says, oh yeah, just double the size of your experiment, and that'll give you the power you need. Which whenever I read that, I think this is obviously something that I've rarely seen. So in many cases, people usually in the real world sometimes have to settle for a power or precision that's lower than what the textbook says, which typically tends to be around 80%, simply because there's not enough time or money or raw materials to do enough experiments. Okay, so usually means when I've worked on these problems, usually it means whenever there's a run budget, it tends to be maxed out, and it tends to be maxed out in a single pass through of the experiment. And I think that this approach is a little bit suboptimal. I think sometimes it's wasteful, and sometimes experimenters, people actually doing the DOE, sell themselves short because of the fact that experimentation is taught as a one-shot approach, at least in the statistical literature. So now I'm going to go ahead and actually just demonstrate a simple example that hopefully will be illustrative here. And here's a situation I run into all the time. So I'm going to go ahead and assume that we have a 3-component mixture experiment. Okay, so we're blending together 3 things, and we have a run budget of 14 runs. Okay, so not a terribly large experiment. And let's suppose that each mixture component has a range that goes from 0.2 to 0.6 with a total set to 1. So we're really just varying the proportions of these 3 ingredients, but we don't want any of them to go below 0.2, and we don't want any of them to go above 0.6. So somebody just, that reads your standard DOE textbook would likely just, start building a design that has 14 runs because that's their budget, and that's what they're going to use. Okay. So this is, I've seen this more often than not. They'll just build a 14-run design because that's their budget. Here's, what a design might look like. That's a 3-component mixture with 14 runs. I just built this using Design Expert. This gray area here represents kind of the entire 3-component mixture space, with these vertices representing pure blends of the individual components. The inner white triangle represents all of the blends where the lower bounds are 0.2 and the upper bounds are 0.6. So my design space is this white region here, design space, and hopefully everybody can see this highlighter that I'm putting in, this text. So you'd have one run done at each of the vertices here, some runs done at the edges, and then maybe a couple runs done here in the middle. This would be if we want to be able to fit a quadratic mixture model going forward. Okay. Standard design. Now, so what's the problem? Why am I complaining about this? Why did I put together this presentation? Well, in theory, there is no problem, because in textbooks or, in lots of DOE presentations, the final result always seems to come out looking like this, right here. I'm gonna, the red area is my sweet spot. That's and in this case, that's a region where we have little predictive error compared to the edges. Notice how it's always this nice, flat, very large red region where I kind of have a lot of wiggle room. So even if I don't quite hit the middle of that, I should still be okay. And it's very clear. The boundary is very clear. Okay, so as I mentioned, the problems always seem to end up working out like this, and that's fine. I mean, if you did this experiment in one shot like this, and you got something that looked like this picture here, then I would say, everything went well. What usually happens more often than not in my experience is the following. Okay, I don't have this nice red, bright red, flat sweet spot right in the center of my design space. I mean, it's super common that what ends up happening is that there's an optimum at a corner, or a vertex in this case. Or in this picture, it's this little red sliver that's right along an edge. Okay, so obviously, when people see this, they tend to think, oh, maybe if I had experimented over here, I could have possibly done a little bit better. I could have gotten a flatter red region. Maybe I could have gotten an even better optimum than I do here. The other kind of concern I have here is what happens if I move away a little bit from this this boundary here. Is there a very steep cliff on the other side where where I don't have a very robust solution along this edge, or does it taper off nicely as I move towards this edge? The answer is I don't know, and unfortunately, in this case, I used up all 14 of my runs. Okay, so I really will never know unless I can somehow get a larger run budget. So the question is, what now? Well, we had a run budget of 14 runs and we performed a 14-run experiment. Okay. The results in the previous picture show that we may not have fully optimized our process because the maximum occurs at an edge of the design space. So there's a lot of uncertainty along the edges. We don't have as much precision typically along the edges. And of course, we don't know what happens as you just, move a tiny bit away from the edge on the other side. In practice, sometimes there's error when it comes to, blending mixture components. And a lot of times, even if you try to operate along an edge, sometimes you're going to get, runs inadvertently just due to not measuring out the components properly that are just a little bit above the edge. So, this makes me a little nervous. So the question is where do we go now? Well, we could accept the results as good enough and move on. So in other words, maybe this edge area is good enough. Problem is again, it's a very tiny sliver. It's not a very robust solution, and I don't know what happens if I just move a tiny bit outside of the mixture space. You could try to extrapolate outside of the original design space, but we typically don't recommend that because a lot of times the functional form of the model, or the relationship between the mixture components and the response, has a very abrupt change that occurs somewhere outside of your original design space. So we would encourage caution if you were to do that. I've seen people occasionally just throw away the data and start over. Why? Because for some reason people think of this design space as being tied to a single experiment, and they think, well, if I want to change the lows and highs or whatever, I need to do a new experiment. And unfortunately, that's not really the case, and I think has resulted in a lot of waste. So the question is could we have done something else to avoid this situation? I mean, if we had kind of come in with a different mindset, could we have possibly increased our chances of preventing a situation like this? Okay. And I think the answer is yes, and I'm going to talk about a strategy right now of what you can do to when you run into a situation like this. So here's an alternative approach that I almost always suggest to people that I work with in consulting projects. Is if you have a run budget that's not a shoestring budget where it's you have 8 mixture components and you can only do 8 runs, why not instead of doing everything in one shot, why not maybe use 75% of the run budget, kind of keep 25% of the budget in reserve, And then maybe, do the remaining, the 25% of the remaining runs kind of after you've seen what's going on in that first pass through. So the idea would be to do kind of a first pass through of the experiment with most of the run budget, not all, and keep some in reserve. So I arbitrarily chose 75% and 25% as kind of, rules of thumb that have worked for me historically, but that's not always going to be true in every case. So in this previous mixture example, what we could have done is we could have done maybe a 10-run experiment first to get a sense of what's going on. And based on the results, it could have been 10 or 11 runs. There are methods that you could evaluate how many runs you should do. So again, this is, I'm talking about this more at a high level, and there will be details available in publications and in future videos we'll do on this topic. And then based on the 10 runs that we do first, maybe then we can allocate the remaining 4 runs. Okay. So if an optimum occurs along an edge, what we could do is instead of, just giving up, we could allocate, we could kind of reshape the design space, keeping our original data, and then we could basically take the 4 runs that we have in the reserve and fill in that additional space. Okay. Now somebody will say, well, I'm very confident that my optimum is going to be in my design space. I know these lows and highs, and why would I ever want to do that? Well, I mean, if the optimum occurs inside the original design space, you could still allocate the remaining 4 runs inside of that original space for your second pass through. So this kind of allows you a chance to, get a decent overview of what's going on and keep some runs in reserve, to avoid situations where you use up your entire budget and you get a suboptimal result. So here's how I would illustrate that alternative approach. I would start with maybe a 10-run design that looks something like this, where, I do 1 run at the vertices. Now, instead of doing 3 runs at each of the edges here, I would only do 2, and maybe I would only do 1 centroid. This is again an optimal design that I just cooked up in Design Expert. Okay. After doing this, this 10-run design, 2 things could hypothetically happen. Case 1 is that I get an optimum along an edge, and maybe I might need to reshape my design space before I allocate the other 4 runs. Case 2 is this example that we all like, where the optimum is, this nice flat region right here in the middle. Okay. And I'll go through kind of what, what I would personally do in each of those two cases. So let's start with case 1, because that's the more interesting one. So case 1, optimum at an edge or vertex. So you do your first pass through and you get an optimum that's at an edge or a vertex. So in this case, as I say here, the optimum lies along an edge, and it's unclear whether this is the true optimum. It could just be a local optimum within my design space, or it might not be the global optimum. So perhaps the process could be further optimized. As I said before, maybe some people will say, okay, this red region is good enough, so I'm just going to stop. But again, whoops, I don't know why that happened. Okay. So yeah, but the problem is again, I don't know what happens right as I go outside of that space. So it makes me a little nervous. And like I said, historically, what I've seen is many experimenters will stop because the run budget has been depleted, or they'll say, you know what, if I want to change the lows and highs of my experiment, I've got to do a new experiment. And that's not always true. So we performed 10 runs here, and we still have our budget of 4 runs left over. So is there a way to solve this problem without having to start over or settle for subpar results? And the answer is yes. We can augment the original design space and do the remaining 4 runs in the larger experimental design space. And as I said, I'm going to show a lot of pictures here, because I like pictures rather than formulas. So here's kind of an illustration of how this would work. So this is how we would augment the design space. So I'm going to move to a square example here. This gray region represents my operating space, hypothetically anywhere where I could perform an experiment. The blue region here is my design space. That's actually where I'm experimenting. I think, that's really the region where I want to tweak my factors. And the red dots represent, the runs that I would do. So in this case, I think there are a total of 10 runs. You'd be responsible for choosing a design in that blue space. Now, let's say you do this experiment and you get this nice comic book explosion optimum here right at the bottom edge of the design space. And you might think, well, that makes me a little uncomfortable. I think maybe if I had experimented maybe in a region that looks like this instead, I could have possibly gotten a better result. But let's not, start over. Why don't we just simply expand the space and continue experimenting? So here is, this is just the graphic copied over from the previous slide. And then what I'm going to do is basically say, okay, how far out do I want to go to really capture that true optimum? How much further out do I want to go? And what I call this the augmented design space, is this green region here. So basically I'm just taking, it's like, when you take a mouse and you drag a rectangle down, that's basically really all I'm doing here. Okay, as I'm saying, well, you know what, I'm going to keep my original data, but I'm simply going to expand the design space. So the green space, as I say here, is added to the original design space to try to capture the optimum. And then what I would do is, possibly using optimal design, is I would simply just add some more runs to this, mostly I would assume to this green region. So yeah, after we augment our original design space, we add additional runs into the larger design space, that's this entire region here, to try to capture the optimum. You don't need to throw away the data. You don't need to do a new experiment only in this green region. You could keep all of the data up here as long as it's good data, as long as you didn't have any, non-reactions or any explosions or whatever. And then you could simply just tack on a couple more runs and push the space out. Okay, I've seen many cases where somebody would just throw this away and say, okay, I'm gonna experiment here now. You don't need to necessarily do that. Okay, so this is, just to summarize, this is just a little graphical explanation of how, intuitively how this would work. So some key points here before I move back to the example is if we use our entire run budget in one pass, we cannot adapt to unexpected results. And in particular, I want to focus on optima at the extremes because that's something that I see happen all the time, but that doesn't get a ton of publicity in textbooks and the statistical literature. So by keeping some runs in reserve, we can change the shape of the design space as needed. And of course, you don't necessarily need to add one time. If it turns out that maybe you want to do a third small experiment in this region, that would be fine. It's not a you don't only get one chance to expand the space. Of course, there is a caveat. I think I'll mention this a little bit later, but there's a caveat that this you obviously have to be able to change the lows and highs of your design space. If it's very in some cases in some machining applications or sometimes when you're preparing concentrations of reagents, it's not necessarily easy to simply just say, okay, I'm going to change the low, I'm going to change the high. So there is a caveat here as well. So I do want to be objective and just say that there are possibly some cases where this may not be applicable. But what I'm going to do is now I'm actually going to use Design Expert to finish up this mixture example. So return to the mixture example. I'm going to use the concepts that I illustrated in the previous slides and show how this would be done in Design Expert. So recall that we had, a 10-run mixture example and we had a 14-run budget. And this is, this was that case one that I had showed, which was the case where we have an optimum here. So how can we use Design Expert to experiment sequentially here? Okay, we want to let the software, it's nice to look at pictures, but it'd be also nice to see how software can actually do this. Well, we want to expand the design space, presumably to include some of the region over here, just so we could kind of see what's going on with this optimum. Right now, we have Design Expert at 12 is currently out, but Design Expert 13, which is due to come out sometime later this year, for the first time ever in history, will allow experimental design, experimental constraints to be modified after an experiment has been built. Okay, so up to this point, the way that we'd have to do it is you have to basically build a new design with the larger constraints and then paste in your old data. Clunky, I don't like it. So specifically for this situation, we are implementing an edit constraints function that, basically you can click on this button and change the lows and the highs or change any of the multi-factor constraints you have. When you click on this edit constraints button here, what I do is I get a dialog that looks like this, and remember these values were 0.06 before. I'm going to bump up components 1 and 2 up to 0.8, and then what I'm going to do is bump component 3 down to 0. Okay, that's going to expand my design space in the correct direction, so to speak. Okay. So notice this is actually where I'm expanding this space, and this is unfortunately a subject matter issue. It's tough to mathematically say, okay, well, what statistically is the best expansion of my space? This is largely, what you think has the best chance of capturing the true optimum. If you go, if you expand it too little, there's a chance that you're not going to get results that are substantially different from your from the first pass of the experiment. If you expand it too much, you might end up getting, you might be on a boundary that's causing kind of nonsensical responses or just very, very poor responses. So it's a balancing act. And Design Expert 13 will basically say it's going to keep all the original data. As you remember, this was that original design space, but now what it does is it basically just turns this, what was this gray region before, into a white region, which is now part of my experimental design space. Okay, so you could see I have my original data here, but I also have some new space where I want to experiment just to kind of see what's going on with that optimum. So we've expanded the ranges of 2 components, and now what we need to do is we need to add some additional runs to fill the space. Remember, we had 4 runs that were left over. And I'm going to use optimal design to do this. Again, there will be some more guidance on this in the, very shortly, kind of some case studies and whatnot. But since I have 4 runs, I'm just going to use them all here in the second pass through. I can't really expand my space anymore, going in this direction. So I think 4 is probably fine. And I'm just going to say use, add these 4 runs to the entire space according to the optimal criterion here. Okay. And it's a shocker, but the algorithm puts all 4 of these runs, in the new space. And it puts them, because we're assuming a quadratic model, it puts them here along an edge. Now, of course, this is kind of a toy example, and I'll do a real example shortly. But yeah, I mean, this is essentially, like I said, more to show you the intuition, show you the mechanics, kind of how you would think through this. So to finish this up, I'm actually going to stop the example here, perform the additional 4 runs, reanalyze the data, and re-optimize and see what's going on over here. I do make just a point here that you might want to consider blocking if you're going to do the remaining 4 runs here on a different day or on a different piece of equipment, on a different machine, or using different raw materials and whatnot. So as you could see on the previous slide, I just ended up putting these 4 runs in the original, the first block, but you should definitely take into account if that makes sense or not. That's a subject matter call. It's probably safer to create a new block, but that will add an additional run that it'll basically use up an additional degree of freedom, or additionally, use up one of your runs. Okay, so I'm not going to go through the analysis and whatnot, because that I think most people are aware of. Lots of people speak on analysis. I want to focus on just getting their experimental design set up. I'm going to come back to case 2. Which is what happens if everything is okay. Remember, there is a chance that everything goes right, and that you end up getting a sweet spot here. Now the question is did we waste time? Did we really lose anything by doing this? What would you do next in a situation like this? Well, let's say you only do 75% of your run budget or 80% of your run budget, and everything goes well, like in this picture here on this slide. The question becomes what to do if you don't need to augment the original design space. What should you do with those 4 runs that you held back? Well, in my opinion, the strategy should be to allocate the remaining runs in a region around the optimum of the first experiment. So you don't necessarily need to allocate the runs in your original entire, in this entire region here. I mean, there's probably not going to be an optimum that occurs near the vertices. So use this information as kind of prior information when you're allocating these 4 runs. Why? Because adding additional runs near a potential optimum will most likely improve the precision of the design in an area where it matters the most. Okay, so if you had just straight up used, kept the original design space, my guess is you'd probably get more additional runs near the edges or maybe some at the vertices. But what I want to do is I basically want to zoom in a little bit and just collect data where I think it matters the most. And of course, if I did this as a one-pass experiment, I can't do this. So what I would do is I basically say, okay, I kind of have a rough idea of where my optimum is going to be. This is not obviously exact because I only used up 80% of my runs, and I might have some uncertainty there. But chances are, if I'm getting a region that looks like this, it's probably unlikely that I have a big optimum right over here. So notice this black triangle that I inscribed within the original space, I'm going to put the 4 points, within that triangle. And the black triangle is defined as this. So what I'm basically doing is I'm shrinking the experimental design space for the second pass through for my 4 runs. And here's kind of a comparison of all of these approaches. Of course, this is, somewhat of a toy example here, so the numbers are just, just for illustration purposes. But what I did is I compared the 3 approaches here. This is the original 10-run design, and I looked at the standard error at the center of the space because that's where I think my optimum is most likely to occur. Here it's 0.5. If I just allocate the runs in the 4 additional runs in this white triangle, I get a standard error of about 0.43. If I allocate the runs here into this smaller triangle, I get a standard error of about 0.40. So about 10% lower. In this case, it's not a huge difference, but there are cases where I have definitely seen an enormous difference. When a higher concentration of points was put in near some region of interest here. So this is kind of just a comparison here. This is what I had suggested. This might be kind of the approach that most people would take if they just go through this. And this is what we're seeing here. So now what I want to do is I want to go through a real example that's a little bit more complicated, and that's something more representative of what you'd see in the real world, and then conclude with some tips and tricks and kind of some take-home messages. So this is a sunscreen example. So what they were doing is they were formulating sunscreen, and they have a 7-component mixture experiment. In this experiment, what they were trying to do is basically find combinations of these ingredients that go into a sunscreen that result in both an SPF 40 sunscreen and an SPF 70 sunscreen. They wanted to see if they could get a model that can kind of give them both formulations. Even though it's a 7-component experiment, in total, only 3 components along with water were varied. And this should actually say 3 components were held fixed or invariant. So it's really a 4-component mixture, even though there's 7 ingredients going into this sunscreen. Okay, these are the lows that they had chosen. These are the highs, a total of 77 weight percent. The other 23 weight percent were those remaining 3 components held in a fixed proportion. Okay, the overall budget was 30 sunscreen formulations, but what they ended up doing was only choosing 20 of them to perform in the first pass of the experiment. Why? Because, they had reason to believe that, trying to get both an SPF 40 and SPF 70 sunscreen out of a single experiment, it's a pretty tall order. and they were basically seeing what would happen with 20 runs before deciding what to do with the remaining 10 runs. Okay. So this is basically how this design was built using the Design Expert software. And again, I'm skipping the analysis in this case because I think that's, most of the other talks are going to talk about analysis, and it's pretty well covered. So I'm just going to fast forward a little bit. They did the experimental, they blended together these sunscreens. They fit a model, statistical model, and they first optimized to see if they were able to get an SPF 40 formulation. For those of you that are familiar with the Design Expert optimizer, you have these ramps, and the question and the answer is yes, they were able to get an SPF 40 formulation. And once you go beyond 3 components, it's difficult to just look at pictures like I did before. So what I'm going to look at are these ramps. This is how much of component A I want to put in. This is how much of component B and component C and water. And notice how this is kind of nice because my solution is inside of my space. I don't have anything at any of the edges over here. And I get a predicted SPF of about right around 40. Okay. So the answer to that question was yes. The problem is the question is can the data collected under this design produce a sunscreen that's SPF 70? So in other words, if I try to target SPF of 70, the answer is no. I could get up to approximately 48, an SPF of 48 here. And notice here that when I'm looking at these ramps, this is along an edge. This is along an edge. This is along an edge. So it's pretty clear that in this case, I get a solution in the that's at an extreme. And because of these ramps that Design Expert provides, I could kind of see in which direction I need to move. I might want to increase component B. I might want to decrease water. I might want to increase component C. Okay, so we could get about as high as an SPF of 48, but clearly to go higher than that, we need to go beyond the original DOE space, the experimental design space. If I had used up all 30 of my runs, I'd basically be done. I'd tell tell people, I'd say I can get an SPF 40 and an SPF 48 sunscreen. I can't really go up to 70 because I used up my entire budget, and I have to either go ask for more budget or I need to, think of another solution. But what we could do is instead, we could expand the design space here. In Design Expert 13, we'll have this Edit Constraints button when you go and actually look at the constraints. And what I'm going to do here is I'm going to take component A and I'm going to take component A and I'm going to increase it to 3. Take component B and increase it to 15. Take component C and increase it to 3. And then I'm going to set water, which had a lower bound of 63 weight percent. And I'm going to just set it to 0 and say that's going to be the slack component. It's essentially going to fill up, it's going to take the formulation up to 100 weight percent. So, and Design Expert will check to see if your existing data meets those constraints. I don't know why PowerPoint keeps kicking me out of this presenter's view. And if all of your existing data is contained in the new space, no problem. If there are some runs that no longer meet the constraints because maybe you shrunk the space, Design Expert will essentially ignore those runs. Okay. And then what I'm going to do is I'm going to use, an optimal augment here. So I'm going to use optimal design to augment. And I don't know exactly why in this case they chose 7 runs. They did put the new runs in a new block. Possibly they were keeping some runs, as a further reserve just in case, or maybe to do confirmation runs. But in this case, they chose 7 additional runs. Okay. And you can see that this here is the first block. Those were the 20 runs they did originally. And you can see that these are the new runs that they would do that are now in this new design space, this larger design space. Okay, so you can see anything that's highlighted is at a new limit, essentially. It's in the new space. There is one run number 24, that actually got put back in the old space. It may have been at the edge of the old design space. And the reason for that is to tie together the two blocks. Okay. So reanalyze, reoptimize. Obviously, they should still be able to come up with a sunscreen that's SPF 40. But after they expanded their ranges, now they tried reoptimizing, and they were able to get a sunscreen that's SPF 70 here. And they only did it with an additional 7 runs. So now they have one statistical model that can, predict formulations that give an SPF of 40 all the way through 70 in a single model. They don't need to have, 4 different models for 4 different SPFs. They can just do it all in a single model here. Okay, so we're about 40 minutes in, so I'm going to just wrap things up here before we go to the Q&A. I know this may have been a very high-level overview, and there's lots of questions, and I'll be happy to answer them. And for people looking for more technical guidance as to, okay, how do I do this in a more mathematical way? As I said, we'll have, very shortly, we'll have more things coming out for that. So the benefits of sequential DOE: it allows for simultaneous exploration of the design space while maximizing the information that each run provides. It avoids situations where you're stuck with suboptimal results and have no budget left for further experimentation. It increases precision in the regions of high interest. If you have some rough idea of where the optimum is going to be, you can do your follow-up runs in that region. You don't have to do them in the entire space. In my experience, there very little research has been done in this area of DOE. And the few experimenters that I know that do this, do it in a very ad hoc manner. Kind of, I may have showed this in a slightly ad hoc manner just to get the concepts out, but, we'll want to do this in a more maybe mathematical way, so that we could justify our approach using numbers. Most of the research that I've seen on sequential experimentation deals with things like screening, adding runs to increase the model order. So like going from a factorial model to a central composite design, as well as adding and dropping factors. And of course, as I mentioned before, no method is perfect. The caveat here is that this approach assumes that you could actually change those lows and highs without great difficulty, which may or may not be true. So some take-home points. So the major point of this presentation, at least what I'm hoping to get across, is just to encourage people to think about DOE as a sequential strategy with regards to the design space. Stop thinking about the design space as this fixed, set, inscribed in stone area that you can't go away from. Not a one-shot experiment. Even just being aware of this technique can be a huge advantage. From our experience, we generally recommend starting with 60 to 80% of the run budget if possible. Obviously, you have to have some excess runs to be able to do this. Like I said, if you have 8 mixture components and you have not a budget of 9 runs, this may not apply. If there are issues with the experiment, the design space can be reshaped and the remaining runs can be allocated in the new space. And if there are no issues with the experiment, the runs that you have left over can simply be added in a smaller region of interest. They could be left as confirmation runs, or just, if you prefer, just put back in the original space. And this can all be done using optimal design. And Design Expert 13 will allow for factor and mixture component ranges to be changed after a design has been created. We're also going to include a design space augment wizard that'll basically take you through all of these steps. So this is just a preview of what's to come. It's something that we run into so frequently that we've decided, we're just gonna have a more automatic way of doing this for the next version of Design Expert. Okay, so that concludes kind of the main, the beef of my presentation. So I want to thank everybody for listening and joining in. Again, if you have any questions for me personally, you can email me here. But I'm going to just turn it over to Greg here just for a few minutes to talk about training. And then after that, Greg will go ahead and read through, some of the questions that came in during the presentation, or if anybody has any, you can type them now. And I'll try to get through as many as possible. If not, feel free to follow up with us later. So Greg, if you're there.
Awesome. Yep, I am here. Okay, so just some housekeeping information here. Let's see, this presentation, the slides will be up in a little bit after the presentation. We'll get those up on our website at staties.com in the webinar section. And also the recording will be posted up by tomorrow. It usually takes us a little bit more time to process a recording that large. But a little piece of information for everyone, we are offering a special discount for attendees to our DOE Summit, and that is 25% all distance learning workshops. We will send this information in a follow-up email as well, but there's a code right there, is Summit25, to use when you're checking out, and that code is valid until August 31st for any courses attended by the end of this year. And that's a new process for us, this whole distance learning, really going well. So let's see. So for those of you with questions, on the right-hand side, on the menu, there should be a little questions drop down. You can feel free to type in your questions there. And let's start going through some of them. Okay, the first question from Michael Morrow. If you select factor ranges as wide as possible or practical to induce a large signal, do you need to worry about power? If I kick the process as hard as I can and do not detect a change, am I comfortable concluding the factor is not active? What are your thoughts on this thinking?
Yeah, that's a great question. And it's a tricky one because, we've always said that choosing those lows and highs is a balancing act. Unfortunately, at least in my experience, sometimes I've seen that if you go too wide, you basically get, two responses that are similar. They're both close to zero. So if you just fit a straight line through that, it's going to look like there's no response. But if you had chosen, maybe a smaller region within those lows and highs, I wish I had a picture I can show you, there may be a response. So I think the answer is, I hate to say this, but it depends. I think we typically, we would say go as wide as is feasible. I still think that power is an issue because, if you have a very, very noisy process, then even, if you go from the extreme low to the extreme high, whatever change you're seeing could hypothetically be drowned out, if the noise is high enough. So I would say yes, I would still look at the power, even if I necessarily can't really do anything more to increase it, just so that I'm aware of the limitations of my experiment.
Okay. Next question from Krista Witkowski, and she says, seems that some replication in the quote unquote old original space would be useful also.
Yeah, I agree. Our philosophy has been, if possible, always include at least a couple replicates. Partly that's, from a statistical point of view, it's so that can enable a formal lack of fit test, meaning you could actually get a p-value that says, is there any signal that I'm missing? Do I need to go up to a higher order model? But a lot of times, when I'm doing consulting with people, it's always interesting when I ask them and when I tell them, hey, these 3 runs that you did are exactly the same. What is the discrepancy between these 3 results that were hypothetically done under the same settings? Are these discrepancies within what you would expect? In a lot of cases, that really unlocks some hidden sources of error, or it's almost kind of like a diagnostic tool where people say, whoa, what's with this discrepancy? Why are my responses, so different at the same setting? So absolutely, generally we would, you need at least 2 replicates. We recommend at least, 3 to get some amount of power for a statistical test, but 5 is kind of the default that we go with. And obviously the number of replicates is going to be partially dictated by the run budget as well. So I agree wholeheartedly.
Okay. Next question is from a friend of Staddy's, Dr. Leonard Lai. If you use all 14 runs for design, even though sequentially, you would still need runs for confirmation, isn't it?
Yes, that's true. So yeah, that would probably be, I mean, if I wanted to add an extra step to this, we'd probably have to, I mean, with 14 runs and 3 components, I mean, it starts to become difficult, to divide it up into, your original design space, your expanded design space, and confirmation. But I agree. Keeping maybe 2 or 3 runs left in reserve, even after you've expanded your space or done the experiment, would probably be a good idea as well, just so you can do at least a couple of follow-up runs at the very end. I glossed over the issue of confirmation a little bit here, but that's a very good point.
Okay. Next, Chloe McGurk asks, how does this compare to running screening and characterization stages before going for an optimization design?
Yeah, so screening would typically, I mean, typically screening would deal with, in kind of the in classical context, would deal with more of choosing what factors or what mixture components you want to kind of carry over for the characterization stage. At least in terms of what I presented, we started, we didn't really do that. We assumed that the components we had were essentially all active to some extent. And instead of choosing what components to keep or drop, we were choosing, we were tinkering more with what are their lower and upper bounds. So that, that screening step would have been done prior to anything that I mentioned here. Here we were assuming we had kind of a good set of factors or mixture components that we were comfortable with for using a characterization design. But this sequential, sequential DOE in the context that I explained is more of in terms of, are we even in the right region? So it could be that this ties in with screening, but that would have to be explored a little more carefully.
Okay. Let's see. Our next question is from Randy Nides. Could you comment on blocking? Most of the analyses of my sequential experiments, plant tissue culture, I end up analyzing as a single block because the analysis sharpens up quite a bit. So in my work, I view blocks as insurance. I'd like to hear your thoughts on this.
Yeah, when in doubt, block. It's definitely the safer option, especially if there's any sort of fundamental difference to how the experiment's actually being done, like you have to use a new batch of raw material for the follow-up runs. And actually in that sunscreen example, the follow-up runs were put in a second block. What that'll do is that'll guard against any maybe shifts that occur where maybe the follow-up runs tend to run a little bit higher on average than the previous runs. That's why when we do that blocking, I'm actually gonna go back to this here. We see that we actually do one run in the previous block as well, just to kind of tie together, make sure, mathematically everything works out. Now, the disadvantage, of course, is that every time you add a block, you're essentially adding, you're essentially using up one run. So you'd have to do fewer follow-up runs that really deal with fitting the model, because some of the runs would be kind of block runs. So that is a disadvantage, is that, the more and more blocks you add, the more and more degrees of freedom are going to be used up. So essentially you're using up runs for blocking. And if you want to kind of keep the same non-block degrees of freedom, you'll have to add additional runs. But from a practical point of view, I mean, when in doubt, we generally suggest blocking, absolutely. It'll decrease the amount of noise. If you're doing a factorial, you might get more power. If you're doing a response surface design, you should get a more precise surface fitted to your data, and a more accurate surface too, because any systematic shifts that occur between the blocks won't be kind of confused with the factor effect. So yes, agreed.
Okay, George Callaway asks, I noticed you used I optimality. Why and why not other optimalities like D?
Yeah, good question. typically for mixture and response surface designs, the goal of those is usually building a predictive model, meaning a surface that has good precision that we could later use for optimization. And the eye optimality criterion actually it's called the, it deals specifically with optimizing kind of that level of precision that we're gonna get in our experiment. De-optimality would be, I think that would be more appropriate in screening or perhaps factorial designs. But to be honest, if you choose de-optimal or even something like a-optimal, I would be willing to bet that from a practical point of view, you're not going to run into a catastrophe. But we like to use eye-optimality because it really gives you more precision in the middle of the design space while sacrificing some precision along the edges. And when we're doing optimization, obviously we'd like our optima to be somewhere in the middle, so that's why we use I as a default. Some people will always use D because that's what they're comfortable with, and I think in many cases it's not gonna, it might be mathematically suboptimal, but you should still hopefully have a reasonable experiment going forward, even if you choose D versus I.
Okay, our next question is from Arvid Harding. He asked, you started talking about power, but never addressed the power in your examples. Should you not consider the power here also? I know in mixture space, you should look at FDS more than power.
Yeah, so that second statement about FDS is true. For the sake of time, I did gloss over, in this case, we were really constrained by our experimental budget. So, whether we did 10 or 11 runs in the original experiment was kind of, but yeah, that would be something that should be looked at. And perhaps if I do this again, I would at least add one step to check the FDS in this case to make sure we're not totally off. In many cases I see is that a lot of people, they can't really ever get the FDS or power that they're looking for. But I think that by doing things sequentially, where you kind of zone in on the design space, you could increase the power or the precision locally near the optimum to try to address that issue. So yes, I probably should have at least mentioned the FDS for that sunscreen example. So that's a good point.
Okay, let's see. I'm going to combine a couple of different questions here because they're related. The first one was to ask about version 12 and using this in version 12, and then David Fluharty asks, when does version 13 come out?
This can be done in version 12. It would just require you to basically, when you want to expand your design space, to build a new design with the larger space. You could use like a historical data, the historical data feature in Design Expert, and then simply just paste in your original data. So it can be done, and I believe we have an example of that on our website. We have a tutorial that goes through a mixture example. Version 13 is slated to be out hopefully by the end of this year or sometime early in 2021. I would like to just announce, though, if somebody does want to be a beta tester for version 13, we now do open betas, so it will be available on our website. But you could feel free to, just ping me, send me an email, and I can make sure that, you're aware of when the beta comes out. Obviously, it's kind of, it's a tentative version, but if you want to tinker around with it and see if you like it, or if there's any feedback you have for us that would make it more useful for your own work, we're always very happy to hear that. So I did just want to point that out as well. Of course, the beta version is kind of tentative, and it's not, but we're always looking for people to test out and give us feedback kind of before we do the final release, because at the end of the day, we want to put out tools that are going to be useful to the people actually using them.
Perfect. Okay, we've got time for a couple more. This next question is from Shoaib Balkaftain, and he asks, can we augment a factorial design?
Sure. If for example, let's say this kind of goes back to the question that was asked at the very beginning. Let's say you choose your factor ranges on the factorial design to be, maybe too small, and you think maybe some of the upper bounds should be lifted. Then yeah, absolutely, you can simply augment the space so that your upper level of the factorial design is higher, and then you can do another factorial analysis with the. But but what would happen in that case is you would have kind of some of these runs that were left at your old lows and highs, and if those runs aren't problematic, then basically by doing this you'd gain a little bit of extra power, because you're adding some runs to an existing factorial design, but you're still kind of in the factorial spirit, so to speak. So what that would do is allow you to augment the space, but you'd also have some intermediate runs at some of the factors, which would provide additional power. So rather than having to start over, you could just augment that as well. We see this more in response surface designs and in mixture experiments, but this could absolutely be done in a factorial design as well. I'm waiting for somebody to come out with kind of the recipe sheet for how to best do this in every single case, but I haven't seen that yet. I may end up having to try writing it myself.
Okay, let's see. This is from Ori Zaduk. Hi, Ori. For case 2, how does one augment the design in a region that is smaller than the original experimental area? Manually selecting the points?
No, so what you would do is you would redefine the experimental design space. You would basically, in Design Expert, you can actually shrink a space as well. And it's just going to keep some runs that are, they're going to be included in the analysis. They're going to, Design Expert's going to recognize that those runs exist. So maybe I'll just draw a little schematic here. Let's say this is my original space, and I have some runs that are here. What I can do is I can say, okay, I'm just going to move my factors inside of this square. You could just change the lows and highs in Design Expert 12 right now pretty easily. It's still going to keep these runs here. But when you go to do the actual augment, it's only going to put the new runs in what the current design space is, which is this new smaller region here. But it's going to kind of take into account all of these runs that were already done. So the answer is yes, it can be done. And it's easier to do this in response surface designs where you don't have components that depend on one another.
Okay, let's see. We'll do one last question here. Let's see. Manpreet Bhatti asks, when shrinking design space, what is the role of the S/N ratio? Because decreasing design space, there may be a low signal as compared to noise. Any comments?
Right, I agree. I mean, you may have, but the thing is you're still, let's say this is your original space. This is kind of an optimum here. And let's say you're going to build a new space that's around this for the second part of the experiment. You're right. Maybe the signal to noise ratio might not be constant. Maybe it's unusually high here, or maybe it's lower here. The thing is overall, you're still going to be analyzing all of the data. So if the optimum is actually over here, then you can't really do. I don't think you could really do any worse by putting the follow-up runs closer to that optimum. And yeah, so it's basically going to give you more precision where it matters. So I don't really think, when you look at some actual mathematical measures, like maybe power or the fraction of design space, there could be some things you might need to change if you really want to evaluate the designs. But I guess I've, just off the top of my head, I haven't really thought about it too much in a very mathematical way, just because when you're near the optimum and you're shrinking the space, chances are whatever ends up actually happening to the signal there, you should hopefully still be better off if you're roughly near that optimum.
Okay, awesome. Well, I apologize if we didn't get to your questions. We've run over a little bit of time here. I apologize for that, but thank you all for showing up and attending this webinar, and hope to see you on a future webinar. Have a good rest of your day or night, wherever you're from. Thank you so much. Bye-bye now.